Hi everybody. Theodor Kaluza in 1919 noticed that you can use the field equations of GR to describe Maxwell's equations as well, and you can unify both theories using a metric in 5 dimensions. He sent his results to Einstein, who pointed out to him that his model gives a totally wrong order of magnitude for properties related to particles such as the electron. Particles were in the focus of the emerging theory of quantum mechanics, and Kaluza suspected that this sphinx of modern physics would swallow his model. The sphinx came first in disguise of Oskar Klein, and hence the theory is known as Kaluza-Klein-Theory today. Actually, back then, Kaluza himself considered another path. He was suspicious of the constant in his equation, the constant of gravitation. And right so, as I will demonstrate in a moment. But let's focus first on some special aspect of electromagnetic theory and its subsidiary optics. Circular polarized light, aka angular momentum, in the context of particles, usually called spin.
So let's imagine this to be the E-vector of a photon. It's rotating, it travels at the speed of light, and now we'll grab it at its tip. Still moving, still rotating, the E-vector pointing towards the origin, resulting in the field of a point charge. It might as well flip and form a neutral particle.
I call that a localized photon. Such a model gives you not only angular momentum, but orientation of the E-vector to a fixed point in space corresponds to charge, and the existence of a fixed point in space corresponds to a rest system, implying mass. So this simple model incorporates the 3 most prominent particle features: spin, charge and mass.
And there's one more thing, the crucial point for such an object to exist at all. In case of any lateral extension of the E-field, energy density will rise towards the center, as will curvature of spacetime, which in turn modifies the trajectory of the photon. In short, an SO3 type of symmetry will result in a photon being trapped in spacetime, curved by its own energy density. It's a really nice toy model, and I'm certainly not the first one who thought about it. But there's a big problem. The orders of magnitude are totally wrong. Actually, that's the same problem Kaluza had, but his ansatz provides a simple solution too. Let's have a closer look. To unify gravitation and electromagnetism, Kaluza used the formalism of GR, introduced a 5th dimension, inserted the electromagnetic potentials in the metric, and used the constant of gravitation in his equations to get a set of equations, the Einstein field equations, Maxwell equations, and a wave equation for the 5th dimension component phi. And last not least, he got totally wrong results for particle properties. And Kaluza saw the problem for this in what he called the fragwürdige Gravitationskonstante. So we just don't use it. We lose the Einstein field equations, but we gain correct orders of magnitudes for particle properties, and with spin as boundary condition, we will get exact particle energies from this ansatz. As a side note, you can also do without assumption number 1 if you stay in flat 5D spacetime, as I will, since within the formalism of GR it's always possible to embed a curved space in a flat space of dimension +1. This leaves one assumption only. Let's look at some technical details. That's a Kaluza type of metric. Roman letters correspond to 5D, Greek letters to 4D. Delta is some constant to make the potential terms dimensionless. To get the field equations of GR, Kaluza had to identify delta with a constant of gravitation term. That's the field equations in 4D. The Einstein tensor equals the stress energy tensor. Kappa usually is again a term of constant of gravitation. and the 5D equations represent the flat case. So how will I modify? First of all, I will shed off all minor terms in the metric. That's these G alpha beta that stand for gravitational and flat terms that are negligible compared to the electromagnetic terms that are the only ones that remain. And I will operate in an electrostatic approximation, so only electric potential will be used. I will use the 4D equations to get an expression for energy density that I can integrate. And for the curved 4D and the flat 5D equations are equivalent mathematically, I get something important from 5D, an equation for phi that I will insert in the metric. As for the constants in the equations, since I want to solve for an energy density that is based on the electromagnetic potential, I'll have to expand by an appropriate constant that turns E square into energy density, and the inverse of that will replace the constant of G term in the field equations. So this is basically the electric constant. And the modified field equations will look like this. That's of course independent from the unit system. However, one that's particular fitting to this formalism has electric charge given in units of energy. A metric fitting to particles should somehow incorporate the phenomenon of spin. And though there are approaches for that in GR, it's far beyond the scope of this work. Thus, any metric neglecting spin has to be considered approximate. Even then, there are still a lot of approaches for a specific 4D or 5D metric. It's certainly reasonable to restrict oneself to a diagonal metric, and spherical coordinates are appropriate. But fortunately, the details of the metric do actually not matter for particle energy, since a dominating term is based on Christoffel symbols containing the trigonometric functions leading to the term -1 in the Ricci tensor, which somewhat conforms to the reasoning of the toy model and SO3. Still, there's a particularly simple metric giving the dominating particle energy term without any minor terms, and it looks like this, resulting in the standard expression for electrostatic energy density multiplied by function phi. And it's an exponential function phi that allows to integrate a point charge term. So it's time to have a closer look for phi. As already mentioned, I'll operate in flat 5D spacetime, look only for electrostatics, and solve the equation for phi to get an exponential function with the electric potential as argument. A characteristic feature of particles is usually spin. I don't know how to incorporate it in the metric, so I use a semi-classical model for angular momentum to get an integration limit, sigma, that will also have to show up in the exponential. An important point, it is this combination of electrostatics and Planck's constant that brings in the fine structure constant alpha in the expression for particle energy. The integrals over such functions feature the gamma functions with argument plus minus 1/3. I'll put that in the expression for electrostatic energy density, integrate and get a value in the range of 0.1 electron volt, the estimated energy range of neutrinos. Neutrinos are intrinsically neutral particles. However, most particles are charged or composed of charged constituents. You may introduce a charge-related third coefficient in the exponential by requiring energy of a charged particle to be higher than that of a pure point charge. That gives a ground state coefficient called alpha Planck, since it is essentially identical to the ratio of electron and Planck energy. Planck defined as gravitation equaling electrostatic force, that is 1 alpha away from the definition with Planck's constant. This coefficient alpha Planck is exactly the factor needed to recover gravitation from a series expansion of the exponential. I'll use that later. But you may as well turn the line of reasoning around. If a second order term, aka gravitation, should not exceed the first order term, aka an electromagnetic term, alpha Planck has to be the limiting factor in the equations. With the additional coefficient, you get the energy of the electron. Building on alpha Planck as a ground state term, you can get additional energy states. The states are not orthogonal, probably that would not fit too well to special relativity anyway, but you may impose weaker conditions, such as requiring a simple relationship to the ground state term. On a deeper level, alignment of magnetic moment may be involved. Anyway, you will get a converging series of particle energies as function of the fine structure constant, spanning the range from the electron to the delta particle. This is supposed to be an approximate spherical symmetric solution, assuming that the next spherical harmonics works as a suitable approximation of angular terms, will give a second series going from the pion to the tauon. Other factors have to play a role since the series omits some particle states. But anyway, there will be one more well-defined value. The absolute upper limit is defined by the math constants of the model, giving the vacuum expectation value of the Higgs field. So, apart from covering most particles with a half-life longer than a picosecond, this simple model, ab initio, defines the energy range relevant for particles. We use the principles of GR to calculate particle mass. It should be expected that there is a close connection between the equations for mass and those of gravitation. As already indicated, the key is the Planck term in the exponent plus series expansion. I'll do that very quickly. The crucial point is there are two different types of R in the equation, and the red one from the exponential has a limit for real solutions, essentially in the order of Compton wavelength in the simplest case of the electron. You get a term that is still 10 orders of magnitude away from gravitation, but since the coefficients sigma and the difference between the Compton wavelength of the electron and the Coulomb expression are due to spin, which has no significance beyond the Compton wavelength, we'll ignore the spin terms, and all terms except the alpha Planck term will disappear. We'll get a term for gravitation, which by definition gives the exact relation between Coulomb and gravitational interaction for one electron. For other particles, you have to insert the appropriate alpha coefficients for energy. That's a little bit ad hoc, but there's some support for this approach. If you apply the same reasoning to minor terms from the metric, you get a result in the order of magnitude of vacuum energy density and the cosmological constant. Okay, we have now established that objects, according to the toy model of the beginning, should have energies within the particle spectrum. As they are basically electromagnetic objects, we can calculate their E and B fields. And we'll do that for a special case, spin 1/2 related to a 720-degree turn. I'll proceed as follows. E, B and C vectors are perpendicular, but they are pinned to a fixed point. Still rotating, for the calculation I use an incremental alternate rotation of EB, BC and
EC around the respective C, B and E axis. Rotation is modeled via a standard quaternion algorithm. The rotation speed of the three components may differ, and naturally the case of interest for particles is half-integer spin, which will be modeled here by one component of rotation around E, B or C having half the rotation speed of the others. Thus there are three distinct possibilities for half-integer spin. Let's look at their solutions for the electric field. The trace of the E vector encloses a spherical cap of area 2/3, 1/3, 1/3 of a hemisphere, or of the whole area of the sphere if you mirror at the center. I did that here. You get trajectories of the E field that enclose a cone, the blue part of the sphere, which cuts out 2/3 or 1/3 of the surface area of a sphere, which according to Gauss translates to corresponding charges. You may as well attribute the trajectory to the complementary geometry, the white part of the sphere, resulting in three complementary solutions of surface and charge. I'll use these 6 objects as quark-like entities that I may combine to particles. And the simplest combination will be 2 complementary objects with like charge, chirality and phase to give a simple sphere without nodes representing lowest energy. Again, there are 3 versions of these with different internal field distribution and symmetry, and they may exist with possible charges plus, -1 or 0. You can't do that with quarks, particles, but you can with an electromagnetic wave. So this basically reproduces the elementary fermion zoo. And there's a very sensitive test for this model. Combine 3 UDS solutions and calculate their magnetic moment. For calculating the magnetic moments of baryons, you compose the half-integer spin baryons from 3 appropriate orthogonal UDS quaternion components. You will have to check that the spin of 2 components cancels to give total spin 1/2. And you calculate the B field. Like for electric charge, this gives relative, not absolute values. In the end, you'll have to multiply by an energy-related factor. You may get these results as ratio to experimental values. However, it looks much better than it is. I picked only the best values from a much larger set. And so this only demonstrates the possibility to get the correct values. To get a unique solution, we have to take a closer look. And one can do that with the nucleons. They have the same isospin, meaning that switching the D and U components should switch the magnetic moments as well. And that is indeed the case, except for a few outliers that do not conform to spin 1/2. The small print here gives an example calculation. It's really very basic. So for nucleons, there is a unique solution, and comparing the ratios of the magnetic moments with the experimental ones gives a value very close to the order of QED corrections. Unfortunately, it's not that easy when S components are involved. The solution for the nucleons has an interesting structure. U and D components are collinear in the time average. The E and B components are orthogonal at any time. Spin cancels. The combined charge is plus 1/3. This should represent low energy and a particular stable configuration. As for scattering results, starting with low energy limit, one should see the UD unit with its charge 1/3, giving a value of 0.4 in this diagram for the ratio of structure functions from the marathon experiment. With increasing energy, one should detect the usual 3 charges attributed to the quarks of proton and neutron.
And at high energy, you would see identical strength of fields and a ratio of the structure function approaching 1. All in good agreement with the experiments. 2 more short points. First, the objects of this model are inherently chiral, which implies that you will have 3 possible combinations of chiral states when a particle-antiparticle pair is generated. For example, in decays or electron-positron annihilation. The same factor which in the standard model is attributed to 3 color charges. Colors are related to QCD, and while a modified Kaluza model does not seem to have much in common with that, there seems to be quite a close connection of this model with electroweak theory. First of all, electromagnetics is an essential element in both. Chirality and SU2 symmetry are important ingredients. The Higgs energy has a very prominent role in the energy series. And last not least, there are the electroweak coupling constants. The weak coupling constant and the fine structure constant alpha, and they both can be calculated. You equate the expressions for a photon and a point charge energy using the exponential of phi to represent curved space. You can extend this concept to 4D space and get the weak coupling constant, and you can combine both in one equation. The precision, as for all calculations of this model, has a limit in the order of magnitude of QED corrections. So we come to the end, and here's a comparison of the standard model of particle physics with a modified Kaluza model. There's some subtle color coding indicating, among other things, the number of free parameters needed for calculations, 0 on the right side, and the accuracy roughly in the QED range on the right side. That's not necessarily 0.1%, since some of the equations are highly nonlinear. So this modified Kaluza model is still very crude, but it covers quite a lot of effects quite precisely. That was a lot of stuff. If I'd try to pick out what might be the most important point, Kaluza's ansatz for unifying gravity and electromagnetism was spectacular. But the boring conservative approach of ignoring negligible terms, that is gravitation, is a very efficient ansatz for dealing with particles. And you still have all the possibilities to use GR in astrophysics or cosmology, not only by relying on the series expansion introduced here, but also by using the fact that on large scales it's the electromagnetic effects that are negligible.